Here's a graph of y equals 2 to the x. Notice that we have a one-to-one function. All exponential functions are one-to-one, which means they have an inverse. And this one in particular has an inverse. Recall that an inverse function we can reflect or flip over the line y equals x. So if we imagine this line y equals x going through here, we would have the graph of its inverse, which would look something like this. And that function has a name. Hopefully you recognize the name of it just by its graph. And that is a logarithmic function. This particular one is log base 2 of x. That is the inverse of y equals 2 to the x. Let's say this was y equals 5 to the x. Then this would be y equals log base 5 of x. Every exponential has a logarithmic inverse. In general, if we have a function, an exponential function, a to the x, its inverse then is log base a. That is true of every exponential. And every logarithmic function has an exponential inverse. Here's how we convert from one to the other. Log base a of x, a to the y equals x. This double arrow means we can go either way. One of them leads to the other. So I'm going to start with this one. A to the y equals x. Oftentimes, when you're first learning exponents, you learn the phrase base to a power. This is what we call the base of this object. Base to a power. I've used the same lettering over here. Log base a. Base to a power, log base. That's not a coincidence. This is the base for a reason. It's the base of the logarithm that has its inverse. Base to a power, a log of a base, a log base something, is equal to a power. A logarithm is just another way to express an exponent. We read this as the log base a of x. The log base a of x. And one of my phrases that I use quite often is a log equals an exponent. A log always equals an exponent. So when you see this, a log equals an exponent. Okay, here's the exponent. Here's the base. Here's my base to a power. So now that allows me to convert from one form to the other. Here's a little more concrete example. 3 to the 4th we know is 81. How do you write that as a logarithm? Log base 3 of 81 equals 4. In other words, some power of 3 gives me the value 81. What is that power? A logarithm is equal to a power. A log equals an exponent. What is the power of this base that gives this result? 3 to some power is 81. That power is 4. And we can do that for all kinds of things. It doesn't have to be always nice numbers either. What's the log base A of A to the x? Well, I'm going to write that in my other form. The best way to deal with this is to write it as an exponential. Let me go back here for a moment. The reason we have this double arrow, sometimes called a double implication, means one of these implies the other, is to convert from one form to the other easily. If I have this form, I probably need to use this form to do something. And if I have this form, sometimes I need to go this way and turn it into that. And that's just what I'll do here. I'm going to turn this into exponential form. Log base A of A to the x. Well, my base is A, my power is question mark, and that equals A to the x. A to the question mark equals A to the x. Question mark equals x. So what does that mean really? It means if I have log base A and I have the same base right here, they essentially cancel each other out, and I'm left with this. Log base A cancels a base A. That's essentially what that means. Log base 5 of 5 cubed. It equals 3. In other words, 5 to what power equals 5 to the third? That's pretty obvious it's 3. Here's the reverse. Let me slide this down a little bit. I want to squeeze in one more. Log base, I don't know, q of q to the car equals what? Well, log base q cancels base q, and you're left with car. Log base something cancels that same base. Think of this as taking the composition of a function and its inverse. Here's the reverse. Now we have base to a power equals something. I'm going to write this in log form. Log base A of question mark is equal to, what's the exponent? Log equals an exponent. The exponent is log A, base A of x. Here's the exponent. There's where the exponent goes, on that side of the equal sign. So now I'm solving for question mark. Log base A of question mark is equal to log base A of x. Question mark is equal to x. How do you make one side look like the other? Well, they're already identical, except question mark and x are in the same spot. So question mark must equal x. Again, let me go back to the original problem here. Let's look at the problem from the very beginning. Base A cancels log base A, leaving us with just x. Some exponential base raised to the log of that same base, they cancel each other out. This is like square rooting something squared. Or cubing the cube root of something. Multiplying by 7 and then dividing by 7. These are all inverses of each other. An exponential and a log of the same base are inverses. A log and an exponential of the same base are inverses of each other. Back in Algebra 2, you learned some log properties. We're going to do a little refresher on those. Here's the first one. We sometimes call this the log addition or the log sum property. So we have a log of some base of this product, which is equal to the sum of the individual logarithms. Remember that a log is an exponent. A log is an exponent. So this right here, this log base a of x, that is an exponent. That is an exponent. Here's an example. 3 to the 5th times 3 to the 8th. What do we do to the exponents to get 3 to the 13th? I'm multiplying base to a power times base to a power. You've learned a long time ago that you add the exponents. And that's exactly what we're doing here. This is an exponent. This is an exponent. Here is their product, 3 to the 5th times 3 to the 8th. We are simply adding the exponents together. Log quotient property. Log of some base of this quotient is equal to the difference of the two logs. And again, back in Algebra 1, you learned that when you have this ratio of a base to a power and a base to a power, you subtract the exponents, or you can subtract the exponents, and that's where this property is based on. The difference of these two logs. A log is an exponent. This whole thing represents an exponent. This whole thing represents an exponent. I have log base something of this ratio right here, and it says we simply subtract the exponents, which we've done. And then the final property, log of some base. Here I have something to a power. We can move that power out front and multiply that whatever that power is by the log base a of whatever we have. So for instance, 3 to the 8th to the 6th. Multiply the exponents together. I have something to a power raised to another power. It's the same thing as multiplying the exponents. This is an exponent. R is clearly an exponent, and we're just multiplying those exponents together. The three log properties. Make sure that you get comfortable using those. There's things that are going to pop up from time to time that you will need to be able to use these with. Now, we're going to look at those properties a little more closely. Here's sort of the background of why those are what they are. So I have this quantity M, quantity N, and I'm going to say M is the log base A of X, N is the log base A of Y. And we're going to go through some things here. Changing the log form into exponential form, base to a power is this, base to a power equals this. I'm going to illustrate those log properties with X and Y. So what I'm going to do is I'm going to multiply X and Y together. That should be the same thing as multiplying A to the M times A to the M. Same thing as multiplying those. Now I'm going to take the log of both sides. And I don't care what base it is. It does not matter what base I'm using here. Also, I know that A to the M times A to the N, using the laws of exponents, I know it's just A to the M plus N. And again, I don't care what base this is. If I don't put a number there, it's base 10, we assume. It could be any base. Sometimes we just put a little b there to represent a generic base. I'll just leave it blank. So, I have this. Log of xy, the log of A to the M plus N. And actually, on second thought, here's what I'm going to do. I'm going to take the log base A. I'm going to make that the log base A. Because if I make that the log base A, look what I have here. Log base A of this base. Log base A of this base. What happens there? Oh, we got to go back a couple pages. Log base A of that base. And it doesn't have to be A. The point is that it has to be the same. This base and this base are the same. They're going to cancel. So this log base A will cancel this A. And that leaves us with log A xy equals M plus N. Now what's M and what's N? Here's M, log base A of X. Here's N, log base A of Y. And that's where that first property comes from. This is one of the things that you need to accept about calculus is you're no longer going to just be told a formula and say, here it is, go use it. You need to understand where it comes from. So here's a little example of that. We're going to do this with the other two log properties as well. Understand where it comes from. Here's the next one. I'll use a different color. Let's go, I'll use this one a while. We're going to take X over Y. See if we can make that other one appear. So I'm starting with the same setup here. I've got M and N We turned those into exponentials. And now I'm going to take x divided by y, divide the left-hand sides, which means I'm going to divide the right-hand sides. And I know that's equal to a to the m subtract n. Take the log base a of both sides. You should see what's coming next. Ooh. There we go. What's coming next? Log base a cancels a. Why are you doing that? Log base a of that ratio is equal to m subtract n. And we know what m is. We know what n is. And we have our second log property appear. Log of a quotient equals the difference of the two logs. For the third property, all I need is one of these. So I'll just rewrite this. Let m equal log base a of x, which means a to the m is equal to x. Now what we're going to do is take both sides, and I'll do it in this order, x to, I'll just call it some power n. No, I don't want to use n. I'll call it some power, I think they used r in the book I got this from. So I'll use r, and then that means I take that side to the r power. So I have x to the r equals a to the m times r. Take the log base a of both sides one more time. Cancel log base a with a. Well, oh, why are you doing that? Log base a x to the r. On the right-hand side, we're left with just mr, but we know that m is equal to log base a of x. I'm going to put the r in front of it, though. Switch the order. R times log base a of x. And that's where the third property comes from. So we get our three log properties by starting with an exponential form, taking the log of a convenient base, and ending up with the property we're looking for. Let's put those properties to work. Let's calculate this. Calculate this, and give you a few moments. hit pause if you'd like. See if you can figure this one out on your own before I show you how to do it. Okay. First thing to notice, we have a subtraction sign. Our goal is to condense this down as far as possible. We have multiple logs, try to get them all down to the same log. So let's see what happens. First, we need to have common bases. Base 2, we're good. Log base 2 of 80 over 5. 80 over 5 reduces to 16. Now remember what a log is. This whole quantity here, this whole quantity equals an exponent. 2 to an exponent is equal to 16. And that exponent is 4. This whole quantity reduces down to the number 4. We started by writing this as a ratio, dividing, and then asking ourselves, what power of 2 is equal to 16? And that power is 4. Let's do one a little less numerical. Something like this. Let's do, this one. Log A to log B minus 3 log C. Addition, subtraction. Well, we go left to right in order. So we do this first. Oh, let's make it interesting. Let's make that C squared. Let's make that, no, scratch that. Let's leave it alone. 3 log C is fine. So we need to do this first before we do the subtraction. So let's put these together. Log of A, B squared. Ask yourself where that B squared came from. Log property number 3. Remember, we go forwards and backwards with an equal sign. Minus log C cubed. Ask yourself where that 3 came from. Now we have a subtraction sign. Log A B squared all over C cubed. Are the parentheses necessary? No. To me, they're helpful. Not necessary, though. Helpful, not necessary. So that's using your log properties to simplify an expression. if there's no base given, we assume it's base 10. And now here's our base e. I had mentioned in the last video, base e, the exponential function, e to the x, is used quite often in calculus. So is natural log of x. Log base e is called natural log. Sometimes it's called naturalis logarithmic, which was translated into ln. Makes perfect sense. Natural logarithm. One of the stories behind that name is because e to the x is used in a lot of real world situations, its inverse also has a lot of natural world properties, hence the name natural log. I don't know if that's entirely correct, but I'll go with it. So whenever you see ln of x, that is the same as log base e. All those log properties from before apply to ln also. And I'm not going to write all of them, but for example, ln a, whoa, that's wrong. ln of a times b, yes, it's ln of a plus ln of b. And so on. Just because it says ln does not mean we need something brand new. The only difference is ln means it's log base e. That's it. It's the only difference. Let's solve an equation. Solve for x. E to this power is equal to 10. First thing we have to ask ourselves, what base allows us to cancel this base right here? In other words, I'll go off to the side here. Over here, if I had 2, I don't know, x minus 3 equals whatever, 12. And I want to get that power, I want to get that variable out of the power, I would have to do log base 2 to both sides. Because that allows me to take this, cancel that, and then I would have just x minus 3 is equal to log base 2 12, and I would go from there. What eliminates a base e? Natural log. Natural log of both sides. The natural log of base e cancels. If we go back to, I believe, yep, if we go back to this one, log base something cancels that same something base. Well, natural log is log base e, which cancels base e. So now we're left with 5 minus 3x equals ln of 10. Those of you reaching for your calculator, put it down. Put your calculator down. You don't need it. Subtract 5 from both sides. Divide both sides by negative 3. And there's an answer that you need to start getting used to. That is an exact answer. Natural log of 10, subtract 5, all over negative 3. That is an exact answer. Not an approximation. That is an exact answer. Could you do an approximation? You could. But one of the things you're going to need to get used to is exact, precise. This is an exact answer. You're going to have to get used to things like ln of 10 showing up in answers. Just like when you had to do in terms of pi back in geometry. You didn't always punch in 3.14. Sometimes you just left pi as pi. Well, quite often you're going to need to leave natural logs as natural logs. I want to do another equation. Nope. Come back to that one. I want to do one more equation. Kind of going the other way. Let's look at, there we go. Log base 6 x plus 1 plus log base 6 x is equal to 1. Let's use our log properties. I have log of something, log base 6 of something, plus log base 6 of something. Put those together. And we put them together by multiplication. This quantity gets multiplied by this. And now we've turned 2 logs into 1. Now we apply our conversion. We have log form. Let me back up here. Here we had exponential form, and we had to turn it into log form. Now that we have log form, we turn it into exponential form. Base to a power is equal to this. Base to a power is equal to this. We have log base 6. Log equals an exponent. Here's our exponent for that base. And then everything else is on the other side. And now we simply solve for x. And this is something we all can do. -3, +2. And no, you're not done. You are not done. Come back up to the top. Plug -3 in for x. Plug -3 in for x. Log base 6 -3. In other words, 6 to what power equals a -3? What power of 6 equals a negative number? There's a power of 6 that is equal to 3. It's not a nice number, but there is a number. What power of positive 6 equals -3? There is none. The domain of logarithm is the range of exponential. The domain of logarithm is the range of exponential. Let me go back, all the way back. Here, domain of an exponential, negative infinity to infinity. Range of an exponential, 0 to infinity. Remember how inverses work. The way inverses work is the function's domain, the function's range is the inverse's domain because we're switching x and y. The function's range is the inverse's domain. So you can only give positive reals to a logarithm. The range of logarithm is negative infinity to infinity. And that's reflected in its graph. Let's go back here where I graphed it. Here's y equals log base 2 of x. This is a vertical asymptote. All the y of it, this falls forever, this rises forever, slowly, but it rises forever. So it uses all the y values. It uses all the possible y values for its range. But for a domain, nothing to the left of 0 can be plugged into this. Its domain is positive reals. So let's fast forward now to our problem. X has to be a positive real number. Negative 3 does not work. Negative 3 does not work and has to be thrown away. So when you are solving logarithmic equations, be careful, be aware of things that will give you a negative value. Now, that does not mean you automatically throw away negative numbers. Does not mean you automatically throw away negative numbers. Let's say I have this in an equation. Whatever. Now negative 3 works. 3 subtract negative 3. Well, that's positive 6. That works. Negative numbers are not automatically failures. You have to plug it into the original problem and see if you get negatives anywhere. Here we got a negative. Had to toss it. Here, if we came out with negative 3 as a possibility, it would be just fine. So we have to be careful with the values we get. Check them with the original problem. Last but not least, natural log is a very slowly growing function. Natural log of x versus x to the n. Natural log of x always loses. If n is greater than 1, x to the n always wins. Natural log of x grows atrociously slow, which makes sense because e to the x grows quickly. If a function grows quickly, its inverse grows slowly, and vice versa. So, a few values here. I'm going to punch these in to my calculator that I'm holding in my hand. You can check some values as well. Natural log of 1. And that makes sense because e to the 0 is 1, so natural log of 1 should be 0. That's kind of a boring number. Let's kick it up to 100. Natural log of 100. Should use approximately. Only 4.6. So I go 100 spaces over. No. I go 100 spaces over to the right. I've only risen about 4.6. Not very fast. Not very fast at all. I don't want to put a scale on there because I'll mess it up. 100,000. You go 100,000 steps to the right, you only go 11.5 up. Not a very big number. A billion. Natural log of a billion. We just broke 20. 1 billion steps to the right. .7 steps up. This grows very, 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 very slowly. That's not even a good representation. Very, very, very slowly. Here's one. We'll say this is 100. We'll say that's 1,000. This might be 100,000. This might be a billion. Not a very fast growing function at all. But yet it's used in many, many applications. Because e to the x grows so fast, ln of x grows extremely slowly.